Hey y'all, my name is Jack. I am an organic chemistry tutor at the Math and Science Center at the Learning Communities at Belmont. So, I am going to be talking today about the different types of bonds that we see in organic chemistry. And we're also going to be going over IMFs, which are intermolecular forces, because those bonds that are not really technically bonds are just as important. But first we're going to go and talk about the covalent bond. The covalent bond is what you will see most commonly in pictures. You have the covalent bond indicated by this line right there. That's what a covalent bond is indicated on in a picture. The covalent bond is just when electrons are shared between like these two carbon atoms, and a bond is entropically favorable, which is an energy term that some of you may have heard in thermodynamics. And so an important part about the covalent bond is that there are two types of covalent bonds. This is also called a sigma bond, or abbreviated like the sigma symbol. That's a sigma bond. That's the primary covalent bond in between those two carbon atoms. But now we can have a carbon double bonded to another carbon, and this is a double covalent bond. But what's important to note is that one of these is a sigma bond, and the second one is a pi bond. A pi bond is weaker than a sigma bond, and once you're adding the pi bond in, you're preventing rotation around the atom. I unfortunately don't have an artistic side really, so I can't really draw what these orbitals are looking like, but there are plenty of resources that give you a more electron space filling diagram so that you can kind of understand why it does not rotate. And then you can have a carbon triple bonded to another carbon, and for usually convenience, we put the sigma bond in the middle, and then one pi bond on the upper bond right there, and then another pi bond right here. So a triple bond is made up of two pi bonds and a sigma bond. It takes more energy to break that sigma bond than it does for those two pi bonds as well, just like as what we saw here. Covalent bonds are very common. You will see them almost everywhere. You can see them in anywhere that you see a line, like carbon, a CH3 bonded to an OH. That would be a covalent bond right there as well. I think it's also, so now we're going to switch over to IMFs. You may have heard of another type of bonding called like ionic bonding, which we'll cover because understanding IMFs is essential to being able to understand how ionic bonding work. So we're going to switch over to IMFs right around now. Sorry about that, little error. We'll change colors even better. IMFs, which stand for intermolecular forces. So by the name intermolecular, it's a force experienced between two molecules. So it's not an intermolecular force isn't going to be present here within a molecule, like between these two. It'd be present in between two molecules, but there are many different types of intermolecular forces that we're going to go through. So the first one, the most simple one that almost every single molecule has, is called the van der Waals forces. So these are primarily found in hydrophobic molecules. Hydrophobic meaning that they don't have any polar functional groups to make them soluble in water. Another important thing is that, so for an example of a hydrophobic molecule, you could have a CH3, and I'm going to be using traditional notation that you'd see in organic chemistry, where there's carbons and hydrogens bonded here, but we omit them. So this would be a hydrophobic molecule because we don't have any polar groups that make it hydrophobic. Van der Waals forces are always present here because they just are. It's happen we see them. They're the weakest. They're the weakest of all the intermolecular forces. Their electron density, so you have electrons scattered throughout this molecule essentially, or like placed along this molecule, and when another molecule, let's say the same thing, approaches, the electron density might change, and that change in electron density is what gives you these van der Waals forces. This accounts for lipid solubility in organic solvents, because like dissolves like is something that you will learn that's extremely important, and it really goes into detail. That kind of covers the basis of how you would dissolve a compound in another compound. You can't dissolve something that's like water and oil. Water and oil don't mix because water can hydrogen bond and is very polar, whereas oil, which is a lipid, does not have those polar functional groups, so they can't mix. And a big part of that all comes from these van der Waals forces. Van der Waals forces are also they are also in polar molecules as well. They just are not as they don't account for as much. They don't really do as much as the other polar aspects of intermolecular forces will do. So another thing about IMFs is IMFs are, just to be clear, they are not a physical bond. They are an attraction between molecules, because you're not actually getting a covalent bond in between them. You're getting an attractive force that's bringing them together. And yeah, that kind of wraps up van der Waals forces. Next, we're going to move on to, let's see, dipole-dipole, which is kind of fun. Dipole-dipole is when you have permanent transient, well, it's permanent transient charges, well, not really transient, but permanent, but not fully discrete charges on a molecule. So this can be seen in a molecule, like, okay, so we're gonna look at CH3 bonded to an OH. So this can be seen where, like, obviously they don't necessarily use these colors, but it's this symbol. These symbol right here indicates that there are like a semi-charge on the molecule, and these occur because of unequal sharing of electrons. So this is in regards to the electronegativity of an atom. Let me just finish writing that. The electronegativity of an atom is how much it wants to pull electrons towards itself. So something that has that negative charge there, the oxygen is much more electronegative than the carbon. It wants that, it wants those electrons to pull this way. So you can always know if there's a dipole present when you see these. And an important thing, because again, this is going over the different, it's about bonds that are, intermolecular forces, about attractions in between molecules. You would then see, like, let's say we have a carbon double bonded to an oxygen. We'll have a cute little molecule like that. and then we'll have the same one. But the thing is that these are oriented, they would be oriented like this in physical space, because remember, this is all physically happening just at a atomic level. You have the positive and negative charges that are attracting towards each other. And a lot of IMFs are always indicated by dashed lines. So the carbon, because it's more, it's less electronegative than the oxygen, would be attracted to that oxygen portion. So this is how they would more so line up in space. A super important part of the dipole-dipole bond is a subset of bonds from that, which is the hydrogen bond. The hydrogen bond is, we can thank the hydrogen bond for a lot of stuff, because we are 70% water, so we kind of rely on a lot of this, a lot of these intermolecular forces going on here. So the hydrogen bond is like a dipole-dipole with what we talked about here, except a hydrogen bond occurs between only an oxygen atom, a fluorine atom, or a nitrogen atom. So what that would look like would be OH, FH, and NH. So these right here would be portions of a molecule that are able to hydrogen bond. Again, you have the electronegative like area on this side that's pulling those electron towards it, and then here's that more electropositive side. And that's all those, and that's all those. This is extremely important for solubility in water, because water can hydrogen bond, and that's where you get a lot of hydrophilic portions of molecules, is spaces where you can bond to other like polar groups. So to show that water is capable of hydrogen bonding, you have that electronegative oxygen and that more electropositive hydrogen, and you're and there you see like and another important thing just to quickly mention about dipole-dipole is that you can actually draw the dipole of a molecule. So again, we're going to go back to this carbon double bond oxygen with these here. A dipole would be indicated by a line that points towards the electronegative, that electronegative symbol right there. And yeah, so that covers dipole-dipole and hydrogen bonding, which are hydrogen bonding is one of the most important things that you will come across in any sort of organic chemistry or anything like that. The last one that I want to go into is ion-ion bonding, which is also known as ionic bonding. These are full discrete charges. That's different than these like transient dipole charges, because, and you can see this with again, color I'm just using because I think of positive as blue and negative as red, but you'll see a symbol like that next to a molecule. So, and this is also really prominent in salts, and is also accounts for water solubility, because of ion dipole bonding that I'll explain in a second. So let's go over this really quickly. So these are R groups. That's just a group of anything that is attached. Nitrogen only wants 3 bonds. That's something to just know. So since it has 4 bonds, it's actually positively charged, and it does not necessarily like to be in that position, but sometimes it just is in that position. And then we have a carboxylic acid that is deprotonated right there, and that you can see has a full set of electrons right there. And those are very strongly attracted. That's why salt does not melt very easily. It's because those bonds are so hard to break apart. And another important thing about intermolecular forces in general is that it takes thermal energy to separate bonds that are stronger. And this is, and to explain a little bit more how ionic bonds are water soluble, it's in regards to ion dipole. So again, the that electronegative oxygen from the example that we did up above here would be then attracted to this positively charged, and that's how you get water solubility. This here would be attracted to that because that negative and positive and those opposites attract. Another important thing is that any molecule with a negative charge is called a anion, and a positive charge is called a cation. And just to kind of go to give a final little review of especially strength, we have ionic bonding, that is the strongest. Then we have the hydrogen bond. Then we have dipole, and van der Waals forces. And this is the order of increasing strength. So yeah, I hope this video was helpful, and you can always come and talk to us if you need any more help in the Math and Science Center. Thank you.